I'm going to go over the answers for the 4.4 quick check. Now remember, on the 4.4 quick check we are looking at strong acids and bases in soluble salt solutions, and we're going to do in this problem here a strong base and a soluble salt solution, but would work for strong acids. And then we're also going to be doing some weak acid base, and we're going to concentrate on just the weak acid. So when we learn how to do a weak acid, we could extend that to a weak base pretty easily. Now what we're not going to do are insoluble salts. We're not going to do an example of that. There won't be one on the test, and we'll learn more about that another class. So first problem, if we were given a solution of barium hydroxide, find the pH and pOH. So first step of that would say, okay, we know barium is Ba2+, and we know that hydroxide is OH-. So that tells us a couple things. First, it's a base. Because we know our list of strong acids and strong bases, we know that barium is going to be a strong base, which means it's going to dissociate completely. So if we do that reaction, we'd say barium hydroxide, BaOH taken twice, and that single arrow is going to turn into Ba2+, and 2 OH minuses. And that's a key piece, the fact that we get 2 OH minuses. We're given in the problem that the concentration of the barium hydroxide is equal to 0.0010 molar, and since every one of those barium hydroxides breaks up to give 1 barium and 2 hydroxides, then very simply the barium ion concentration is going to be the same as the barium hydroxide, 0.0010 molar, and the hydroxide concentration is going to be double that, so 0.0020 molar. It's a little sloppy, but 0.0020 molar, just because there are 2 hydroxides for every 1 barium hydroxide. So we keep talking about that would be like a sandwich, and for every 1 sandwich you get 2 pieces of bread. So if we started with 0.0010 for the barium hydroxide, we get 0.0020 for the hydroxides. Now, once we know the hydroxide concentration, finding the pH and the pOH should be pretty easy. And if I know the hydroxide, I'm going to go ahead and figure out my pOH, because we know that that is the negative log of the OH- concentration. And so using my calculator, I find out that that is going to be 2.70, and the pH is simply 14 minus the pOH, and that's going to come out to be 11.30. So my answers here, the pH is 11.30, the pOH is 2.70, and I got that from knowing my hydroxide concentration, and I got that because I knew that my barium hydroxide concentration, doubles to give you my hydroxide. So once I know the OH, I get the pOH, and I can get my pH. Now the second problem on here has to do with a soluble salt, and this is aluminum acetate. So again, we have to go through this idea. Aluminum we know is Al3+, because we memorized our ions. And we know acetate is C2H3O2-. So if it's a 3+ ion and a 1- ion, the compound is going to be Al C2H3O2 taken 3 times. Now what happens to that is, again, acetate substances, we know our solubility rules, acetate ions, make a substance very soluble, so this will completely dissolve, and when it does, we're going to get 1 aluminum ion, aqueous, plus 3 acetate ions. So we get a 1-to-3 ratio. So, in the problem, we are told that the concentration of our aluminum acetate is 0.0010 molar, and if that breaks up to give us 1 aluminum and 3 acetates, then the aluminum ion concentration must be the same as the aluminum acetate concentration initially, so that'll be 0.0010 molar. And my acetate concentration will be 3 times that, so 0.0030 molar. And that's the answer. Find the concentration of all the ions. So when the aluminum acetate dissolves, we will get aluminum ions, and we'll get 3 times as many acetate ions. Now the next problem is talking about the weak base, and this is hypobromous acid. Now we learned all our different ions, so the hypobromite ion is BrO negative. You will also see this written as OBr minus. So the hypo, a lot of times they turn that one around. So BrO minus or OBr minus, you should recognize both. And on the answers that we gave out, we called that OBr minus. So the formula for this could have been written as HOBr. And that actually makes sense because when you write out the compound, the H really is connected to the O, which is connected to the Br. But we could write it both ways. Now, we learned our strong acids, and we're going to find out that this one here, since that's not on our strong acid list, it must be a weak acid. So that means that we have a double arrow, that only some of these break up because they break up into ions, dissociate into ions, but they also go back together to be the original acid. So they break up and go together, break up and go together. So we have to treat this problem totally different. Now we have a 0.01 molar solution, so I'll put that in, 0.0010 molar solution. And initially we're saying that we're not putting in any H plus or BrO minus, and that's going to be the way for all of our problems, that we just start with our one compound. And some of this is going to break up. So what we're going to do is say, let's just say X amount of this breaks up. So this would be minus X. And this is our initial concentrations. This is their equilibrium concentrations. And this middle row is our change. So we're going to say that X HBROs are going to dissociate, so that's X. And on the other side, if we are breaking up a certain number of HBROs, then we must be making that same number of H pluses and making that same number of BrO minuses. So every time one acid molecule dissociates, we get one H plus and we get one anion BrO minus. So at equilibrium, we could expect this to be 0.0010 minus X, and 0 plus X, this would be X, and this would be X. So at equilibrium, these are our 3 values. Now, we need a clue on how much this breaks up, what's the value of X, and that clue is given by the Ka. Now the Ka is the equilibrium constant for this reaction, so we could say Ka is equal to the expression, the products over the reactants raised to the powers of their coefficients. So the H plus ion concentration times the BrO minus concentration all over HOBr, or HBrO. And that is going to equal, what do we say, 2 times 10 to the negative 9th. Pretty small. Now, we can substitute in our expression. So we have X and we have X. So the top of this is going to be X squared over 0.0010 minus X equals 2 times 10 to the negative 9. Now at this point, you might see that this is going to turn into a quadratic formula, but we do have our simplifying assumption. And we are going to assume, this is a really good assumption, that X is much smaller than 0.0010. And we know that because this is a very, very tiny number. And we can go back and check this in a minute. So if X is much smaller than 0.001, then the value, let's say therefore, 0.0010 minus X, that expression is really almost exactly the same thing as 0.001 molar. So not subtracting that x is really not going to change our answer very much. But what that does do is it simplifies our expression so that now we say x squared over 0.0010 is equal to 2 times 10 to the negative 9. That's a much simpler problem to solve. So we can see 0.001, that's 10 to the minus 3 times 2 times 10 to the minus 9. So I'm saying x squared equals 0.0010 times 2 times 10 to the negative 9. And if I multiply that, I'm going to get 2 times 10 to the negative 12, because this is 1 times 10 to the minus 3. I'm going to add my exponents as I multiply. So 2 times 10 to the minus 12 equals x squared. What we're interested in is x, so that's the square root of x squared. So that's the square root of 2 times 10 to the minus 12. Now, we can kind of do this in our heads, you know, that the square root of 10 to the minus 12 is going to be 10 to the negative 6. Now the square root of the square root of 2, I would have to kind of do that with my calculator, and we're going to be, that's going to be 1.4. So x, which if we go way back up here, we say what is x? X is our H plus concentration. It's also going to be our BRO minus concentration. But if it's our X plus concentration, is 1.4 times 10 to the minus 6 molar, then we could go ahead and figure out what our OH is going to be, our pH is going to be, because that's a negative log of the H plus concentration, which we know is going to be between 5 and 6. So we need to use our calculator for this. We find out that it's 5.85. So here's one of our answers. What's the pH of this solution? Now the other question is, what is the percent dissociation? How much? We say this is not dissociating very much. So of all this that started, how much of it actually is dissociating? So we really want to say is, you know, x divided by 0.0010 times 100. That will give us, these two numbers here will give us our percent dissociation. So let's go back down to our numbers. Now we know x over the initial value will give us our percentage times 100. So that's 1.4 times 10 to the negative 6 over the initial concentration, which was 0.0010 molar, times 100. And when we do that calculation, we find out that that is only 0.14%. That's much less than 1%. So when we said that the amount that x, you know, that broke up, you know, that we could ignore that because it's very small, is very true. That only much less than 1% of our acid dissociates. So this would be a very weak acid. Now we also know that it's a weak acid because of the fact that our Ka was a pretty small number. And that's how we do the quick check.